Everybody knows that one of the best ways to really improve your Web3 security game and learn about new types of exploits and vulnerabilities is by reading audit reports from other firms, other solo auditors, and audit contests as well. And the best takeaway that you can get from reading any one of these reports, any specific finding, is that you can start to understand the exact mindset that the auditor was in and exactly what sort of heuristics you might be able to use to uncover these vulnerabilities into your own audits. But of course, that is often quite hard to do given that the auditor is not necessarily explaining the finding in such a way that people will be able to learn from it and see how they can find it, but rather just so that they can communicate the actual finding and explicate the criticality of the bug or vulnerability. And additionally, of course, there's also a lot of context that you'll need on the particular system to really understand how the bug came about and what exactly you could use to sort of track this down on your own in your own security research. So in this video, I'm going to change that, and we're going to go over 3 findings that I personally had in several past Guardian reports, and I'm going to explain the headspace that I was in and the heuristic that you can take away from that and be able to use in your own security research, reviews, audits, contests, whatever. And of course, if you're a Web3 developer and you're working on a protocol, these are 3 more bugs that you'll want to look out for when you're designing and building your system. So after watching this, I hope that you come away with this with some takeaways, and of course, 3 new interesting bugs and types of bugs, really bug classes that you can look for and try to uncover. All right, but first of all, who am I and why should you care about the particular findings that I uncovered? Well, of course, my name is Owen, and over a year and a half ago, I founded Guardian Audits, and ever since then, we've uncovered dozens of critical and high vulnerabilities from auditing easily over 100 different smart contracts with over 1,000 hours spent auditing personally. And my goal with all of these videos, and especially this one, is to help you become a lot more skilled at Web3 security, whether you're looking to become an auditor or really you're just a Web3 developer looking to improve your all-around security game. Then I want to help you do that while avoiding all of the mistakes that I made along the way. All right, so without further ado, let's get right into the 3 findings here. Okay, so we've got 3 different findings to dive into today, and I'm really just going to start off by diving straight into the first one here. All right, so our first finding here is NMKT3, and it is titled Griefing Name Sellers. Now, before we read over the description here, let us go and actually just have a quick look at the corresponding code and just get some high-level context here. So of course there are 3 functions that we want to focus on for this finding. This is enter bid for name here, then we have accept bid for name, and we have withdraw bid for name. So the people who put up a name, which is, you can basically think of a name as just an NFT for our intents and purposes here. So I can put up a name for sale and then people will bid on it. And if I want to accept the bid, I, as the owner of the NFT, will call accept bid for name. And then if I'm going to be bidding on a name, an NFT, I can enter bid for name, but I can also withdraw bid for name. Okay, so those are the 3 functions we want to look at here. And really the key here is that when I enter a bid for a name, what's happening is, of course, we're checking the existing bid for the name. There can only ever be 1 bid at a time for a specific name. And then what we can do is we can choose to overwrite that bid, the existing one, if we have actually provided a higher message.value, right? So if we're willing to pay more for the name, then we get to overwrite this existing bid, right? And we do that with this line here. And of course, if we don't provide enough message.value, we will enter this check here and we will revert if we didn't provide more than the existing bid. So of course we have to bid more than whatever the existing bid is, but notice of course that we have this third function here, we have withdraw bid for name. And what this will do is this will basically, as long as I am the person who has that highest bid there, then what I can do is basically cancel my bid, withdraw it, and then get the amount back that was sent in for the bid. And of course, if your bid was overwritten here, then you're still able to claim your bid amount with this pending withdrawals mapping. So the issue here is that I can actually, as soon as I see that there's some NFT, let's say the name Bob for an NFT is put up for sale, and then somebody bids on it, let's say they bid 10 Ether, and let's say that I owned the NFT name Bob, and somebody bid 10 Ether on my name Bob, that's what I would consider. I'd consider that's a good price, right? Or, maybe you think Bob is worth a lot more, but me personally, I would be willing to sell that for 10 Ether. So as an owner, I would want to accept that bid. But what can actually happen is somebody, a third actor here, can come and enter a bid for 11, and so they overwrite that bid for 10, but then they can immediately, literally even in the same transaction, if you're using an attack contract or something like this, they can immediately withdraw that bid, and essentially the bid that was previously there and was at 10 Ether, that bid will have been overwritten, and when I withdraw this bid, then that bid doesn't get reinstated or anything like that. So essentially now I, as the owner of this NFT name Bob, instead of being able to accept my 10 Ether bid, then now when an attacker comes in and basically just overwrites that bid and then withdraws, now there is no bid for me to accept. And so the buyer wasn't able to buy at 10 Ether, and the seller, me, I wasn't able to accept that bid for my name. And of course, somebody could even set up some sort of MEV type bot that would automatically front run, back run, sandwich attack, whatever, any sort of bids or listings and stuff like this, such that when somebody puts up a bid for, let's say, my name Bob, then I can immediately back run that, and in one single transaction essentially erase the bid and do an enter bid for name at literally even one way higher, and then immediately withdraw the bid. And so if we just briefly read the description here, it is simple for a malicious actor to grief a seller by placing a bid higher than the previous and then withdrawing the bid or transferring the token to another address. As a result, any bids made with true buying intention are lost and the seller is unable to sell his name. And then of course there are a few possible solutions to this. You could somehow reinstate the previous bid, although that does get a little bit messy. And of course, if you're only looking at the very last bid, then there are of course ways to grief that as well. But then also you could require that there are a few blocks necessary before you're able to withdraw your bid. And then this actually entirely mitigates the single transaction sort of griefing vector, and also requires the attacker to actually, have their bid there and have to wait before completely taking that money off the table. And so they expose themselves to real risk of the owner actually accepting that bid, right? All right, so on this finding, what is the takeaway? What is the heuristic that you can use in your own audits to be able to uncover similar attack vectors? What's the tool that you can use to start to uncover things along this sort of vulnerability class? Well, there are two things that really mix together to produce this vulnerability, two things that you can actually look for and combine them yourself in different ways to find similar findings. And that is, first of all, the act of overwriting a piece of state, right? So we were overwriting this previous bid with some sort of newly created bid, and then also front running, back running, all sorts of, MEV style attacks or things like this. So in this case, we combined the fact that we're overwriting this name and then able to, of course, risk-free withdraw it and basically zero out the bid with a potential front-running or really a back-running attack vector in this case when somebody, as soon as they enter a bid. I find that front-running and back-running, or a combination for just a sandwich attack, is often something that developers maybe don't consider their protocol being used in such a way. And so it's an attack vector that I can actually usually find that there's something interesting that comes of it that is not desired by the protocol developers. So I always like to think especially with functions like this, what sort of advantages can I get if I were to immediately backrun this? And let's just assume that you're able to easily get guaranteed, like in the very next transaction, just for the sake of, building out a POC and trying to understand what the risks are. See what are the possible advantages of doing that, and then also how does that negatively impact others, right? So in this case, the particular person who's doing the backgrounding here, it's not clear immediately how they're benefiting from this, but they are immediately griefing the person who's trying to buy the NFT and the owner who actually is trying to accept the bid, right? But then, of course, on a secondary sort of look, what can happen is if I see somebody bidding 10 Ether, then I can go and, erase that bid with the back running technique. And then I can put in a lower bid. Maybe I want to be able to buy an NFT name at a lower price. Well, if I can erase everybody else's bid and only let mine be there, and then now I no longer have an existing bid to have to one up, now I can put in bids that are lower and potentially get mine accepted. So always look for special ways that you can sort of combine state manipulations, especially state overwrites like this, with any sort of front-running, back-running attack vectors like we did here. Okay, and number 2 here, finding number 2 has to do with GMX, and particularly GMX v2. This particular finding is from the 3rd GMX synthetics audit that we did, and this particular finding is global 2, and it has to do with blacklisted addresses. So to understand a little bit of the background for this, I've pulled up the codebase at about around the same commit as what was done in the report here. But of course, I'm only going to look at the areas that are specific for this particular vulnerability. Of course, I highly recommend that you go and watch the GMX v2 overview video on this channel if you want to really understand this attack vector and this vulnerability in depth with all of the context around GMX v2. So this finding is mostly concerned with this token utils library and exactly how they're handling the transferring of tokens. First of all, what we're going to do is we do some validation and early returns and stuff like this, and then we get some sort of gas limit. That's all great. And then we basically go into this helper function, which is a non-reverting transfer with gas limit. Okay, so we scroll down, we find this helper function. And so we're calling a token and we're using the transfer selector. This is all fine. And we give it a certain amount of gas and we get either a success, which is either this actually was a successful execution or execution reverted. And then we get some return data. And with ERC20 tokens, the return data for the transfer should be a Boolean, right? Indicating false or true, this transfer succeeded or not. Or of course, some of them revert, and then of course some of them just return false always, which is which is wonderful. But this function here, essentially, if you can imagine what would happen if we had a blacklisted token, depending on the implementation of the blacklist, either this is going to revert and we're going to get a false here, in which case we will come down here and return false and have some return data there. Otherwise, the implementation might just return false, in which case we're going to have success. So we're going to go in here, there is going to be return data, and then it is going to be greater than 0. And so when we decode it as a bool, we're going to, assume that this, whatever this token is, it's trusted and it's a good implementation that actually has a decodable Boolean here, and then it is going to decode to false because we are trying to transfer to a blacklisted to address here. And so ultimately, in this case, we will end up returning false and return data. So ultimately, no matter which implementation of the ERC20 token, we're going to return false in both cases. Okay, great. So we go back up to our transfer function here, and we see, okay, so success is going to be false. So we do not return, and we end up parsing a revert message. And again, we assume that, we trust this implementation and that this isn't going to be some nasty return data that ultimately ends up some sort of revert happening. But then we are going to actually revert with a token transfer error. So why does all of that matter? So we're going to see in just a second why this is actually a huge, huge problem. So first of all, let's get some context on the system as a whole, right? So GMX v2 allows you to open positions, perpetual positions that say if I want to long ether and I want to hold a position that has 10 ether in size because I think ether is going to go to the moon or something like this, then I can open a position, have that position open, and I have some amount of collateral. If my position makes huge losses, for whatever reason, FTX goes under, people start talking about orgies, ETH goes to $800 or something like this, something absolutely catastrophic. Now, when the losses of my position are essentially so large that my collateral that I put down to basically back my position can no longer sustain it, then the keepers at GMX have to come in and they have to liquidate my position, right? They have to be able to say, you should have added more collateral to this, or you should have decreased some of the size of your position. But now since we've gotten to this point, we have to liquidate you, right? So when they liquidate us, basically they're going to make a decrease order on our behalf. Now it is a slightly special kind of decrease order, but it uses the same general code path and logic as a decrease order. So why is this important and what does it have to do with this transfer function reverting when somebody is blacklisted? So what happens is in decrease order utils, you can see that what we end up doing, either if there's two tokens that are possible outputs, or if there's only just one token that's a possible output, we're going to end up transferring out to an order.receiver, and we're going to transfer out all of these tokens. So let's focus in on this case when there's only one token to transfer out, because this is the simplest, by far the easiest to understand. What we're doing is from a market token, which is actually holding all of the tokens that need to be transferred out to this receiver, we're transferring out output amount of this output token. So let us ask ourselves, what happens here if the order.receiver is actually blacklisted for this particular output token? Well, then of course, any sort of decrease order that comes here and attempts to do this transfer out, which will ultimately interface with this transfer function in token utils, is that order execution will revert. Well, now we literally just talked about liquidations that keepers need to be able to make on the exchange, and that this is a particular type of decrease order. Well, if we have an order.receiver on that liquidation order that is blacklisted for this output token, then this particular liquidation cannot go through. And essentially what you have is an unliquidatable position on the exchange, which can cause tremendously bad debt for the protocol, and essentially remove a good deal of risk for any potential traders, as they can open a position that has barely any collateral at all and be absolutely fine because they literally cannot get liquidated. So that leaves us with a question: what is the order.receiver for a liquidation order? And then how can this be used to actually game the exchange? So if we go into liquidation utils, when we are creating a liquidation order, what we can see is that the receiver here on the order.addresses is the account. So it's the person who owns the position. So how can all of this be used and tied together to exploit the exchange? Well, what we can do is we can open a position for an account that is blacklisted for USDC, let's say, and this can be easily achievable by funding the order vault or the data store from a separate address, and then the funds that came from that separate address in the same transaction, you can do this with an attack contract, those funds are credited for this account. So this account doesn't necessarily have to transfer those tokens into the system. It just has to, those tokens have to get there by way of some other address doing it, and then they can be credited to this account. Now the account can have those tokens as its collateral, and it could also have those tokens as its P&L token, but in this case you would want it to be the collateral. And then voila, you literally have a position that cannot be liquidated as long as the keeper actually is trying to transfer some collateral that's left over back to the receiver. And so now I can create a position, it can have significant losses such that it should have been liquidated, because if it were to be closed, the remaining collateral that's left is not nearly enough left to back the size of the position sufficiently. It should have been liquidated, but in this case, since the keeper cannot actually do this transfer, then it can't be liquidated. So then you might be asking yourself, well, if a decrease order cannot go through, then how is the attacker going to actually get their money out, right? Didn't they just lose their funds as well? Well, the order.receiver is modular, right? So there are a few ways we can get around this. First of all, you can just set a different receiver. You can spin up a new hot wallet and have that be your order receiver. And this address is, of course, not blacklisted for that token. So it can actually receive it. This transfer can go through. You could also employ a swap path, and you could still be able to transfer it to the same account, the owner of the position, if we just add a swap path at the end. And so this way, instead of trying to transfer out the token that we're blacklisted for, we will basically swap it within the system, swap it to a different token, and then send that token to our address. And of course, we're not blacklisted for whatever token we just swapped for. And so that way we can open a position which cannot be liquidated in the vast majority of cases, but however, still has all the upside of a normal position. So what are the takeaways here, and how can we apply them to future audits and contests that you do? So obviously, the number one takeaway here is blacklisted addresses. You cannot always assume that a token transfer is going to go through, right? And you also have to understand that we can manipulate and decide whether or not we want a token transfer to go through as an attacker by leveraging these blacklisted addresses. In some cases, you might not even have to own a blacklisted address to pull off the attack. You could actually just reference a blacklisted address, put that as a parameter on, your struct or whatever it is in the system, and leverage the fact that that reverts to be able to exploit the system. In GMX's case, that arose as unliquidatable positions, or even really a slew of other issues throughout the exchange, such as, potential risk-free trades and all kinds of things of that nature, just out of the way that this transfer function could be gamed to revert by utilizing these blacklisted addresses. Okay, fantastic. So here we are, we're looking at our third finding here, and this one has to do with an NFT project. So this is an NFT project that I believe it rewards holders of actual other NFT projects. It's actually been quite a while since this particular report. I think this was easily over a year ago, but nonetheless, this is a very notable finding and something that you can take to actually apply to your own contests and reports yourself. So we're looking at UF4 here, and this is titled Mint Failure. So before we dive in to the actual finding here, let's get some context on the code here and sort of see what does the finding look like in the code. Okay, so I've got a similar commit pulled up to what was used in the report, although this is slightly different, but the bug here is for the most part exactly the same. So I've pulled up the public mint function, which is the function of interest for this exploit, and we can see, first of all, they've got some require statements and validation, and then they've got some, reward distribution logic and things like this. But really the interesting part of this function has to do with these else if cases in this minting here. And really specifically, if we focus in and look at how the IDs of this token ID counter are being handled with the actual NFTs that are being minted, we can see that at any given time, as we're first coming in and entering this for loop for this very first safe mint, whatever the token ID counter currently is what is about to be minted. So if we're, let's say we're on line 22094 here, we haven't entered this for loop yet. The token ID counter, that ID for an NFT does not exist yet. It only exists on these two lines, right? Before we actually increment the token ID counter. So on SafeMint, after this is executed, now and only now does this token ID counter ID actually exist as an NFT. Then we set rewards, that's not important, and then we actually increment the token ID counter. So now the incremented token ID counter, no NFT exists for this ID here. And then we go back in the loop, then we actually mint an NFT there, so now an NFT exists for the token ID counter, and then we increment it again. And now again, no NFT exists for this ID here. So the relationship between the token ID counter and the actual NFTs here, if we look at them, from a inter-transaction level, so not within any specific transaction, the token ID counter will always be for the next available NFT to mint. So really it points to an NFT ID that does not exist yet. So why is that important? So we can see I have line 2084 highlighted here, and you might already see why, is that we have a random number here and we are taking it modulo the token ID counter plus 1. So let's think about this for a second. If I have a counter where it is the number at which there is no NFT here for this ID, and it's the first one, then let's imagine I was just taking modulo that number. Now, if I have any number below that, there is an NFT ID that exists for all of these IDs. But as soon as I get to this number, this is the first ID that has no corresponding NFT. But of course, if we're moduloing by this ID number, then if I get exactly that ID number, it will wrap back around, it will be 0 again. But that is not what we've done here with this modulo. This modulo is taking the token ID counter plus 1. So instead of having the modulo here and everything below it actually exists as an NFT ID, what I've done is I've increased the modulo by 1, and now everything here exists. There's an NFT for it, but there is one existing ID within this group here for which there is no existing NFT. So what does that mean? That means that I can actually, there's a decent chance, if we have a small token ID counter, that I'm going to actually get a token ID here, and I'm going to get an earn2 as a result that actually corresponds to an NFT that actually doesn't exist. So what will happen with when we call owner of course, if we pull up the ERC 721 implementation here, we can see owner of, if we get this owner of and it is 0, e.g. there is this NFT ID has not been minted yet, which can be the case, then we will essentially revert. And so in some cases here, when this earn2 is actually for that NFT ID that has not been minted yet, it's the very next one to be minted when we reach this, then it will actually revert when we attempt to get the owner of to get the send to here. So if we read the finding here, I think it becomes quite clear. In public mint, when performing earn2 equals random modulo token ID counter dot current plus 1, there is a possibility earn2 is equivalent to the token ID counter dot current, which yields a token ID for a token that does not yet exist. Therefore, the subsequent call to owner of will fail and the mint will revert. And so then, of course, the recommendation here is to perform the modulo token ID counter dot current instead of adding this 1 here. And that way it's impossible to get an NFT ID for an NFT that does not exist yet. So what is the takeaway and what's the heuristic that we can use to find this in other code bases? Well, of course, first way we can, literally take the application that if you try to get the owner of an NFT ID that doesn't exist yet, then the transaction will revert. But I think more interestingly, as a class of bugs, there's this classic off by 1 error where in some computation, especially when there gets to be, somewhat complex mathematical formulas, it actually becomes very common that there's an off by 1 error. And especially even with things like for loops, you can often end up looping an additional unintended time. And for this reason, I actually think that off by 1 errors are probably one of the most common bugs that exists in smart contracts. And so it can really, really pay whenever you see some sort of mathematical formula, and especially when you see a +1, to really drill in and focus in and draw it out, write it out on a piece of paper. Or of course, if you have a whiteboard, just write it out on the whiteboard, work through it and see, is that 1 necessary? Or if they don't have a +1, do they potentially need a +1? Because there always seems to be an off 1 error more often than not. All right, fantastic. Those were our 3 findings for today. I hope that you saw something new, something that you hadn't considered before. Maybe you hadn't thought of blacklisted tokens, or maybe front running and back running is not something that you usually look for. Let me know what your favorite finding here was, and let me know if you learned anything new in the comments, or if you had any interesting findings or similar to this that you'd like to share. And of course, if you're working on a protocol and you have some sick DeFi application that you are bringing to market and you're starting to get into the process of looking for a smart contract security audit, then go to guardianaudits.com/course quote to apply for a quote. And when you do, I will do a free first pass high level security rundown of the code base that you share. And I'll share a list of any glaring issues, things that I might fix. Anyway, the documentation or anything like this could be improved, and specific actionable takeaways that should be fixed before an audit. And of course, if you know a team that is looking for a smart contract audit coming up, then of course also send them to guardianaudits.com/quote. And of course, if you're looking for a community of other security-minded engineers, auditors, and even Web 2 professionals who have come over to Web 3 and shown an interest in Web3 security, and if you'd like to connect with other people who are just getting into Web3 and share your experience and learn from the experience of others, and even potentially team up with others from across the world and compete and participate in team audits of real protocols, compiling a real team report and getting rewarded for the findings that you uncover, then go ahead and join us in the community at lab.guardianaudits.com. All right, that is all for this time. I'll see you in the next one.